Aircraft designs have continuously evolved over the years towards higher reliability and safety. Yet, despite all of this progress, failures still happen. Automation embedded in the highly integrated autopilot and flight management systems has earned a great deal of confidence amongst pilots. However, reliable as these systems may be, they still fail. Such an integration of systems makes it difficult for pilots to analyze the cause of the failure, an airplane upset result. The airline must therefore continue to maintain its flight standards training programs that address techniques and procedures necessary to handle all possible malfunction and failure situations. Pilots must be able to identify any failure and promptly take necessary corrective actions. For example, the electrical power generating system and distribution system may degrade controllability and cause displays to blank, which could potentially create a high workload situation within the cockpit. In a demanding environment, such as during a complex approach requiring constant communication with ATC, and where the aircraft is flying through turbulence and rain, a heightened crew awareness is necessary to avoid a situation where the failure goes unnoticed for some time and results in high rates of descent and higher than normal G-forces, leading to an upset. Thus, a pilot must be trained to recognize and avoid this type of situation that can lead to an aircraft upset. The only way to ensure that pilots have the ability to recover control of an airplane that has exceeded the parameter of the normal flight envelope is through training and crew coordination. This cannot be emphasized enough. Simulator training sessions must address instrument scanning techniques and the CRM attitude of obtaining help from the other pilot assessing the situation. Pilots must be trained to prioritize their actions. If an abnormal situation such as instrument malfunction ever arises, the first priority is to fly the aircraft. That means maintaining proper attitude and making sure there is enough performance to maintain a safe speed and altitude. The second priority is to navigate, that is, to make sure that the aircraft is heading towards the desired direction and not conflicting with ATC instructions or terrain constraints. The third priority is to understand and manage the system status. Not complying with this priority sequence may lead to an upset. Seasoned instructor pilots can describe countless situations that were observed inside flight simulators where the crew had their attention diverted from the flight instruments as they attempted to reset some equipment while the aircraft was left to itself, and thus ending up in an abnormal attitude. Despite the remoteness of a loss of all generators, or a double engine failure due to mechanical reasons, either type of occurrence would force the crew to fly based on limited attitude and navigational information. Every operator's training program must emphasize crew coordination in such cases. The flying pilot must have his attention fully dedicated to the basic flight instruments, while the non-flying pilot performs other tasks, such as preparing for approach, configuration changes, and cross-checking for deviations and systems management. This task sharing is crucial for the safety of the flight, and it must be exhaustively trained and trained and trained. Such training cannot be emphasized enough. Every pilot understands that he or she cannot rely on his or her sensory perception alone. What the mind and sensory organs of a human body perceive about a flight environment at times can be very misleading. For example, environmental clues may be misleading when an aircraft is on top of a layer of sloping clouds, or in a moonless night over a totally black terrain, or yet approaching a runway that slopes gradually upward into mountainous terrain. Therefore, pilots know that they cannot rely on their senses, the so-called seat of the pants for instrument-based flying. Instrument flying, as the name indicates, is flying based on instruments and not on your sensory perceptions. The flying pilot must concentrate on his or her instruments and use them as primary information. Understanding aerodynamic principles of a swept wing can make pilots better equipped to successfully maneuver the airplane back to a normal level flight, in the unlikely event of an airplane upset. In the context of aerodynamics, the following three basic concepts should be understood. Pitch control, lateral and directional control. The lift force generated by a surface is a result of angle of attack, the dynamic pressure of the air moving around it, which is a function of the airspeed and air density, and the size and shape of the surface. Lift varies with angle of attack for constant speed and air density. As the angle of attack increases, lift increases proportionally. However, at the critical angle of attack, lift decreases instead of increasing. At this critical angle of attack, the air moving over the upper wing surface can no longer remain attached to the surface and the flow breaks down. This situation is referred to as a stall condition. Remember that the angle of attack is the angle between the relative wind and the chord line of the airfoil, which should not be confused with the flight path angle or the pitch attitude. Pitch attitude is the angle between the longitudinal axis of the aircraft and the horizon, as displayed on the EADI. The angle of attack is the difference between the pitch attitude and the flight path angle. The flight path angle is the angle between the flight path and the horizon. An airplane can stall at any attitude and airspeed, as you can see in this animated video. The pitch angle is sometimes negative, very steep, and yet the aircraft may be in a stall condition. It is not always easy for the pilot to recognize such situation and take the necessary action to reduce angle of attack. When the wings are designed so that they are bent upward, they are said to have a geometric dihedral. The dihedral provides stability to the aircraft by working opposite to the side slip movement, by creating a rolling moment that tends to raise the wing into the side slip. The wing sweepback reacts to side slip very much as geometric dihedral. That is, if a side slip occurs, the sweepback causes the wing to roll. This is because the wing that moves forward relative to the airflow generates more lift and more drag, as it is a more square angle with the airflow, causing the aircraft to roll as well as to yaw back to the no side slip condition. The dihedral effect on a swept-back wing aircraft is typically quite stronger than that of a straight-wing aircraft. This coupling is particularly confusing in dynamic situations, where the side slip angle changes quickly. Consequently, pilots must be aware that rapid application of large rudder displacements or rapid application of large asymmetric thrust changes on such aircraft may create control difficulties. In other words, should an upset occur, the use of rudder should be avoided, except if absolutely necessary to aid roll control. If ever used, it should be used very smoothly, and rudder reversals must be definitively avoided. In general, an airplane stall is characterized by any or a combination of the following conditions: buffeting, lack of pitch authority, lack of roll control, inability to arrest descent rate. A stall in the Embraer 170-190 family of airplane can be identified by stick shaker actuation. Stick shaker will occur before buffet onset. Additional stall protection is provided by limiting the control column authority and the nose-up direction, which is accomplished by the angle of attack limiter. It is important to note that during stall, there is sufficient roll authority to maintain wings level attitude. Pitch effectiveness is not affected during stalls. At high altitudes, the indicated speed may be low even at reasonably high Mach numbers. However, the Embraer 170-190 does not have a so-called coffin corner in its flight envelope, where the maximum operating speed is close to the minimum operating speed. Even at this maximum operating altitude, the plane still allows a reasonable range of operating speeds. But the most important point about stall is, a recovery from an upset should always begin by getting rid of the stall condition. In other words, if the airplane is in a stall condition, the first and foremost thing the crew must do is to get out of the stall condition. If this is not done, other recovery actions may be ineffective. Movement around the lateral axis of an airplane is called pitch and is usually controlled by the elevator. Given any specific combination of airplane configuration, weight, center of gravity, and speed, all forces will be balanced at one elevator position. In flight, as speed changes, the elevator position must be adjusted to balance the aerodynamic forces. Control forces required for this new position can be neutralized by using a pitch trend mechanism. The use of variable incidence stabilizer is usually adopted because of the large range of angles of attack possible with swept-back wings. But you must keep in mind that a variable incidence stabilizer is very powerful. It is very effective because it can achieve large angles. If the wrong setting is used, the pilot not only may face higher than normal elevator forces, but may actually run out of longitudinal control. On the Embraer 170-190, the elevator thrust compensator, ETC function, applies elevator commands to reduce the pitching moment produced when adding or reducing engine thrust. It is a function of N1, Mach number, and pressure altitude. It is limited to plus or minus 5 degrees, and its effect is proportional to the amount of thrust above or below the reference. When the fly-by-wire system is in direct mode, however, to maintain pitch attitude, some manual pitch compensation is required when adding or reducing thrust. The vertical stabilizer and the rudder are sized to control the yawing moment associated with an engine failure at the most demanding flight condition and to generate sufficient side slip for crosswind landings. Aileron movement changes the local angle of attack of the wing, changing the amount of lift and causing rotation about the longitudinal axis. Multifunction spoilers assist ailerons in providing roll control. During an airplane upset, large amounts of roll input may be required to recover the airplane. In an extreme airplane upset, if the target is to arrest a descent, the elevator inputs may not work if the airplane is at a high bank angle or inverted. In those cases, the use of ailerons is essential. Sometimes it may be necessary to use rudder in the direction of the desired roll if ailerons alone are not capable of generating the desired roll effect. The amount of rudder required will depend on the airplane airspeed and the configuration. An uncoordinated rudder movement results in a yaw movement in the direction of the rudder input. This yaw creates side slip, which causes a roll in the same direction as the rudder input. That is a dihedral effect we have mentioned before. When encountering an angle of attack associated with the onset of stick shaker, on the Embraer 170-190 family of airplane, ailerons are still effective at controlling roll. At greater angles of attack, the action of ailerons may not always generate a significant roll momentum. Since the vertical stabilizer rudder is rarely stalled, it is always possible to generate a roll by using the rudder and the dihedral effect. Rudder use, however, must be in a very careful way to avoid side slips and possible high loads on the vertical stabilizer and side slip conditions.